All right, we are at section 32.6, power in an AC circuit. Let's share the PowerPoint, and there's a equation already up there that doesn't belong there because the original publisher's PowerPoints had an error and I had to fix it. I'm not sophisticated enough with PowerPoint to know how to cycle through the equations properly, but we'll just get started. The power, the instantaneous power is equal to the instantaneous current times the instantaneous delta V. All this is lowercase because it's AC. I max and delta V max, those are the DC equivalents. That's why they're in capital letters. So P equals I delta V equals I max sine omega T minus phi times delta V max sine omega T. Multiply that out, you get P equals I max delta V max sine omega T sine omega T minus phi. Now we're going to use a identity sine omega T minus phi equals sine omega T cosine phi minus cosine omega T sine phi. So we make that substitution into the equation above. We get power equals I max delta V max sine squared omega T cosine phi minus I max delta V max sine omega T cosine omega T times sine phi. Now we're going to use some facts about the let me erase these so that you'll see it when we get to it. We're going to use some graphs to show that sine squared omega T is equal to 1/2. And why they use this substitution, I don't know, but they use it. Sine omega T cosine omega T equals 1/2 sine 2 omega T, and the average of sine 2 omega T equals 0. Well, and you'll see the average of sine omega T cosine omega T equals 0 also. So I don't really understand why they use the identity, but we'll go with it. Now, where does that come from? Let's share the PowerPoint. Let's get a new share and share the PowerPoint. Not the PowerPoint, the iPad. It takes a little while, and you'll see here we have I used Mathematica to actually plot these. Now, sine squared x is equal to sine x times sine x, and you can see that what is the average? Well, if we take the 0.5, whoops, I've got the eraser. If we take the 0.5, the average, well, it's a little slanted, but we'll fix that. Come on, there we go. Is that about right? The average of sine squared x is equal to 1/2, just like they said. Now, here's the sine x, or sine omega T cosine omega T. I just used x, it's the same thing. And the average is right here at the 0. Come on, straighten out. That's good enough. And the same with the 1/2 sine 2 omega T, or sine 2x. It's 0 also. So now let's go back and look at, now you understand where they made these substitutions. Sine squared omega T average is equal to 1/2, and the average of sine omega T cosine omega T, or sine 2 omega T, is equal to 0. Well, if that's equal to 0, then this whole term on the right side of the minus sign turns into 0. So all we're left with, and the sine squared omega T turns into 1/2. So the average power, since we're using averages, the average of sine squared omega T is equal to 1/2, and sine 2 omega T is equal to 0. The average power is equal to 1/2 times I max V max cosine omega T. Let me say that again. P average, the average power, is equal to 1/2 times the maximum current times the maximum delta V times cosine phi. Well, that cosine phi is what we call a power factor. Now we're gonna we can see a little graphic here. The total voltage delta V max makes an angle phi with I max. Okay, now let's look at this. P average equals IRMS delta VRMS cosine phi. Well, that doesn't look like the last one. There's a 1/2. What happened to the 1/2? Well, I'll show you what happened to the 1/2. let's go to the back to the. Sorry for all the switching, but I can't write on the PowerPoint. I guess I could have written some equations, but it's easier just to do it on the iPad. So let's look and see if indeed they're the same. So we have P average is equal to IRMS, VRMS, cosine phi. That's what they gave us. Well, what is IRMS? IRMS is I max over the square root of 2, and delta V max, delta VRMS is equal to delta V max over the square root of 2, cosine phi. Now, if you have the square root of 2 and the square root of 2 in the denominator, those both multiply to 1/2. So that the average power is indeed equal to 1/2 I max delta V max cosine phi, just like they say the P average is equal to IRMS delta VRMS cosine phi. Now let's go back to the PowerPoint and finish. So we know that this equation is right. P average is equal to IRMS delta VRMS cosine theta, where not theta, phi. Cosine phi is equal to the what we call the power factor. Now, look at the delta V. That's this horizontal section, and that's equal to V max cosine theta. It's the adjacent vector on the V max vector, and that's equal to I max R. The delta V I max delta VR is equal to delta is equal to V max cosine phi. Okay, so now cosine phi we can see is equal to it's the adjacent over the hypotenuse, so it's I max R over delta V max. Well, well, first of all, what is delta V max divided by I max? It's equal to Z. So I max over delta V max is equal to 1 over Z. And so we get the cosine phi is equal to R divided by the impedance. I say Z. Z is the impedance. That's understood. So P average is equal to IRMS, VRMS, cosine phi, and the well, if cosine phi is equal to R over Z, we have I squared delta V RMS R over Z. Well, delta V RMS over Z is equal to IRMS. So the average power is equal to I squared RMS or IRMS squared times R, which we already know that from our DC. Well, I mean, it was P is equal to I squared R. Okay, so, and we also know that power is equal to I delta V, so P average is equal to IRMS delta VRMS. Okay, now we know that energy stored in an inductor is 1/2 Li squared. Now, and we know that P average is equal to IRMS delta VRMS cosine phi. So if most of your load is inductive, just as such as in motors and stuff, you've got a lot of power loss, and so in many applications they add a capacitor to change the phase angle, so you get a higher, more of the energy, more of the power is transferred to the dissipative load of the circuit. So they can, they add a capacitor to kind of balance it out. Let's see, where are we? Okay, now here's a quick quiz. An AC source drives an RLC circuit with a fixed voltage amplitude. If the driving frequency is ω1, the circuit is more capacitive than inductive, and the phase angle is -10 degrees. Now, if the driving frequency is ω2, the circuit is more inductive than capacitive, and the phase angle is +10 degrees. So -10 degrees if it's capacitive at ω1, +10 degrees if it's inductive at omega 2. At what frequency is the largest amount of power delivered to the circuit? Now, in order to answer this, you have to remember my little San Antonio Transit Authority, not San Antonio Transit Company. That's the one that works. San Antonio Transit Company, where the first quadrant is sign is positive. Let's go around the circle. SAT, C at A, all of the functions are positive, sine, cosine, tangent. In the second quadrant, sine is positive. In the third quadrant, tangent is positive. And in the fourth quadrant, cosine is positive. So the cosine of minus 10 degrees is equal to the cosine of plus 10 degrees. They're both positive in the first and fourth quadrant. So the same amount of power is delivered to both. There you go. Same amount of power is delivered to both because the phase angle minus 10 cosine of minus 10 degrees is equal to cosine of 10 degrees by the fact that the first and fourth quadrants cosine is positive in both cases. And we're going to get to resonance in the next video.